On behalf of 24houranswers.com, I welcome you to today's lesson. In this video, we're going to look at the second derivative test. And the second derivative test involves the second derivative, and it's another way of helping us find maximums and minimums on some function. In all honesty, we're going to be getting the same exact answers as we got back when we did this same exact function. We had the same function that we're going to do right now yet again, but in a previous video we applied the first derivative test. And the first derivative test, we found those critical values, a critical value in which we will call C. That's what most books call it. That is a value that makes the first derivative equal to 0. As a matter of fact, if you look back at the intervals of increasing and decreasing, that's where we first introduced or talked about the critical values of this function f of x. So I'm using this same function so that you can follow along and learn these concepts all while applying it to the same function. And then in later tutorials, we'll combine all this stuff together with different functions so that we can find maximums, minimums, intervals of increasing and decreasing, intervals of concavity, all of that stuff combined together. So before we dive into this example, I'm going to go ahead and tell you I don't find myself using the second derivative test anywhere near as often as I do the first derivative test. However, should you run across an example where your instructor says determine maximums or minimums using the second derivative test, this is the concept we will take. We want to find a critical value. A critical value is a value, we'll call it C, such that the first derivative is equal to 0. Then we can take that critical value, you can plug it into the second derivative, and if that second derivative at that critical value is less than 0, you have a maximum. And basically what this means is the function is concaving downward. Concave down looks a little something like that, and there's our critical value. Notice we do have a maximum. Vice versa, here we find that critical value. Again, that is a value that makes the first derivative equal to 0. Plug that value into the second derivative, and if you get a positive value, then you're going to have a minimum. And if the second derivative is positive, that means we're concave up at this critical value, and notice we do have a minimum right there. Now it goes without saying, if the second derivative at that critical value is equal to 0, then we cannot apply this test because it's not going to be greater than 0 or less than 0. Or if the second derivative at that critical value does not exist, therefore we cannot apply the second derivative test. Since you have seen this example in several videos already with the first derivative test, intervals of increasing and decreasing, intervals of concavity, we have already found the first derivative and we found the critical values of -8 and 2. These are our two C values. The second derivative, relatively quick to find. All we're doing is taking the derivative of the first derivative to get this. And now let's apply the second derivative test. We take this critical value, f double prime of -8, and we plug it into our second derivative, and all we care about is the sign. But if we take 2 times -8, we get -16 plus 6, we get a -10. And I'm going to change that to a blue color here because notice our second derivative at this critical value is less than 0. When your second derivative at that critical value is less than 0, we have a maximum. So we don't have to do any sign testing on the left side or the right side like we did in the first derivative test. I guess you could say that's one benefit of the second derivative test versus the first derivative test. So therefore, we are guaranteed to have a maximum when x is equal to -8. Now that's the same concept as the first derivative test. Now let's come and let's plug 2 into the second derivative, f double prime of 2. So we take 2 times 2 plus 6 and we get a positive 10 right here. When the second derivative at your critical value is positive, then we have a minimum, guaranteed. And back in the first derivative test video, we took those two values, we plugged them into the function, and we've already seen this graph over in Desmos. I'll just reiterate that in this video as well. But when we plug the critical value of -8 into the original function, f of x, that's going to be our maximum value, and it's going to be a local max in this case. And when we plug 2 into the original function, there's our minimum right there. So rounding these y values off to the nearest tenth, this is our max, this is our min. And to make sure we understand this, here's those same two values. Again, we talked about this back in the first derivative test, but let's apply that second derivative test. Let's understand what the second derivative test is telling us. We've already said we have a max here based on both the first derivative test and the second derivative test. But what the second derivative test is telling us is this. Notice the function is concave down right here. Well, that means the second derivative is going to be negative throughout this spot right in here. And the second derivative we found was negative when x was equal to -8. Hence, when the second derivative at a critical value is less than 0, you have a maximum. Now, when the second derivative is positive at a critical value, notice our function's concave up throughout here, right? So when x is equal to 2, our second derivative was positive, implying that we have a function that's concave up. And since this is a critical value, that means our first derivative is equal to 0. Combining all these concepts together, we have a minimum right here at 2, -17.3. And there you have it, the second derivative test. Again, I used the first derivative test more than I use this, but this is actually not a bad example to apply the second derivative test because the critical numbers are relatively easy to find. The second derivative is real easy to find, and we can plug in those values, in my opinion, faster than maybe creating a number line and testing separate values both on the left side and the right side of our critical values like we would have to do in the first derivative test. And that's it for this video. I hope it helped. Be sure to check out our YouTube channel for more videos. Links to our social media are in the description below.